Hello there, my dear friend, my fellow traveler of time. As the world outside settles into a quiet hush, and the soft glow of the moon begins to paint silver shadows on your windowpane, I invite you to join me on an extraordinary voyage. There's no need to pack a bag, no need to even lift your head from the pillow. All this journey requires is for you to do one simple, wonderful thing: take a deep, slow breath. Breathe in, and feel the gentle calm fill you, from the tips of your toes to the crown of your head. And as you breathe out, let go of all the little worries of the day. Let them drift away like tiny dandelion seeds on a soft breeze. Because tonight, we are not merely going to sleep. We are going to embark on an adventure, an accelerated trip through the deepest corridors of time. Our destination: a period so ancient it defies imagination, a world both alien and profoundly familiar, the Pleistocene epoch, better known to us all as the Great Ice Age. But to truly understand the Ice Age, we can't just appear there. No, that would be like reading the last chapter of a magnificent book without knowing how the story began. To appreciate the frozen grandeur of that world, we must first witness its fiery birth. So, hold on to that feeling of serene stillness. Let your consciousness become light, a tiny, shimmering vessel of thought, ready to travel faster than light, faster than time itself. Our journey begins not thousands, not millions, but 4.5 billion years ago. Can you feel it? The gentle pull backwards. The days, the years, the centuries are peeling away like the pages of a cosmic calendar flipped in reverse at impossible speed. Millennia become whispers, and entire ages blur into fleeting moments. We are speeding back, to a corner of our galaxy, the Milky Way, where our sun was just a young, vibrant star, still learning the rhythms of its own stellar life. And around it, a planet, one among billions of countless other planets, was just beginning to stir from the cosmic dust and gas. What would we see if we peered out the window of our little dream ship right now? What does a planet look like in its very first moments of creation? Forget the gentle blues, the swirling whites, and the earthy greens you know so well. In this primordial dawn, what we witness is a vision from a fever dream, a spectacle of raw, untamed creation. Before us hangs not a world, but a roiling, incandescent ball of liquid metal and searingly hot rock. It glows with an inner fire, a furious palette of crimson, molten gold, and angry orange, a shoreless ocean of lava under a sky that knows no blue. Listen. Can you hear the symphony of this newborn world? It is not the gentle lapping of waves or the rustle of leaves in the wind. It is the thunderous, chaotic roar of planetary formation. The surface of this infant Earth is a terrifying, mesmerizing canvas of constant change. Rivers of lava, brighter than 1,000 suns, carve glowing canyons through plains of cooling, blackening rock. Volcanoes, not as mountains but as gaping wounds in the planet's thin skin, erupt without cease, spewing fountains of fire and plumes of sulfurous gas into the oppressive atmosphere. The very geography of this world shifts in the blink of a cosmic eye, a chaotic dance of creation as the planet slowly, violently, begins to form its internal structure, separating its core, its mantle, and its crust. And the sky, oh, the sky is a terrifying theater of celestial violence. This early age, which scientists would later name the Hadean Aeon, a name fittingly derived from Hades, the underworld of Greek myth, was defined by an event called the Late Heavy Bombardment. For hundreds of millions of years, our young planet was under constant, relentless assault from the heavens. Asteroids of all sizes, leftovers from the solar system's construction, rain down in a perpetual storm of fire and impact. We see them now, great mountains of rock and ice, streaking through the blackness, their arrival marked not by a splash, but by a cataclysmic explosion that vaporizes rock and throws up tidal waves of liquid magma. Each impact is a planetary-scale drumbeat in this violent, creative symphony. Now, let's bring our dream ship a little closer. Let's try to imagine the atmosphere, the very air of this place. If you were to take a breath here, which, of course, we are thankfully only doing in our imaginations, it would be your last. The air is a thick, heavy, toxic blanket, a noxious cocktail of gases that would be instantly lethal to any life form we know. It is choked with carbon dioxide, nitrogen, water vapor as steam, and poisonous compounds that hiss from the volcanic fissures. And what's missing? What is the one crucial ingredient for our own lives that is nowhere to be found? Oxygen. There is virtually no free oxygen here. It is an alien world in the most profound sense. No plant, no animal, not even the tiniest microbe as we understand it, could possibly survive on this beautiful, terrible hellscape. This was the Earth, our home, in its first age. It feels eternal, doesn't it? This fiery, violent ballet seems as though it could go on forever. But the universe is a place of constant, gradual change. This first eon of Earth, the Hadean, lasted for an almost incomprehensible 500 million years. Think about that for a moment. If the entire history of modern humanity, from the first cities to today, was just one single second on a clock, this Hadean eon would be a full day. It is a span of time so vast that our minds can only grasp at its edges. Yet, even this immense age had to come to an end. Slowly, painstakingly, as our dream ship hovers and watches over millions of years, we see a change. The cosmic bombardment, the rain of asteroids, begins to slow down. The relentless storm from space subsides into a less frequent drizzle, and then, finally, into a calmer sky. With fewer massive impacts churning its surface, the planet has a chance to cool. A crust, at first fragile and constantly broken, grows thicker and more stable, like the skin on a cooling cup of cocoa. The wild, primordial hell begins to quiet down, its fiery rage softening into a deep, steady glow. A new eon, a new chapter in our planet's story, is about to begin. The stage is being set for the first, quietest, and perhaps greatest miracle of all. The roar is fading. The deafening, percussive symphony of asteroid impacts and bursting lava bubbles that defined our planet's infancy is quieting down, replaced by a profound, planet-wide silence. We have drifted across an immense gulf of time, leaving the Hadean eon behind to enter a new age, a new chapter in Earth's grand story. This era, lasting an almost unimaginable 1.5 billion years, would one day be named the Archean Eon, the ancient or beginning age. And here, in this vast stillness, the world is preparing for its most subtle, yet most significant, transformation. What has changed? As we gaze out from our vessel of consciousness, the world below is still alien, but the incandescent fury is gone. The planet has had time to exhale its primordial heat into the cold vacuum of space. The surface, no longer a sea of liquid fire, has solidified into a dark, brittle crust. It is a world of rock. But something new is happening, something truly wondrous. The immense quantities of water vapor that choked the Hadean atmosphere, trapped as superheated steam, are beginning to condense in the cooling air. Imagine the first raindrop. Not a gentle pitter-patter, but a heavy, sizzling drop falling from a thick, hazy sky onto a still-hot rock surface, instantly turning back into a hiss of steam. Then another follows. And another. Soon, it is a drizzle, then a downpour, then a deluge of biblical proportions. For thousands, perhaps millions of years, it rained. It was a rainfall unlike any our world has known since, a relentless, world-covering storm that washed the toxic residues from the sky and began to fill the vast, empty basins of the newly formed crust. And so, the oceans were born. Watch with me as the water pools, gathers, and swells, forming vast, dark bodies of liquid water that stretch from one horizon to the other. But do not picture the sparkling blue oceans of today. These primordial seas were different. Rich with dissolved iron and other minerals leached from the volcanic rock, they likely shimmered with an eerie, olive-green or brownish hue under the dim, filtered sunlight. The water was warm, almost like a global bath, heated from below by the planet's still active core. Between these strange, silent oceans, the first continents had formed. But they were not the familiar shapes we know. They were smaller, scattered landmasses of dark volcanic rock, located in entirely different places than they are today. And as we drift over them, what do we see? Nothing. Absolutely nothing. The land was utterly, profoundly naked. There was no soil, only crushed rock and dust. There was no grass, no moss, no flower, not a single green shoot to be found anywhere on the land. And without plants, there were, of course, no animals to graze upon them. The silence on these continents was absolute, broken only by the sigh of the wind, the distant rumble of a volcano, or the shudder of the ground as tectonic plates, the great puzzle pieces of the Earth's crust, slowly ground against one another, pushing up the first mountain chains. There were no witnesses to any of this magnificent, lonely geology. The atmosphere, too, was still alien. While the rain had cleared some of the haze, the air was still a thick brew of nitrogen and carbon dioxide. And that crucial element, the one we are breathing so peacefully right now, was still missing. There was almost no oxygen to be found. So you might ask, in this quiet, barren, water-filled world, was there life? For a very, very long time, the answer was no. The planet was a beautiful, sterile sphere of rock and water, a stage fully set, but with no actors. But life, it seems, is patient. And in the right conditions, it is perhaps inevitable. Where did the miracle happen? Not on the harsh, dry land. Not in the deep, dark abyss of the oceans. It happened, most scientists believe, in the shallow, sunlit waters near the shores of these ancient continents, or perhaps near hydrothermal vents on the ocean floor, where heat and a rich soup of chemicals provided the perfect laboratory. We don't know the exact moment or the precise recipe. Perhaps it was a chance encounter in a warm little pond, a lucky chemical handshake between complex molecules. But at some point, a collection of atoms learned to do something extraordinary. It learned to make a copy of itself. The first spark of life had been struck. And what did this first life look like? Forget lions and eagles and butterflies. This was life at its most humble. For hundreds of millions of years, the only living things on our planet were microscopic, single-celled organisms. They were simpler than any bacteria we know today. But they were alive. They grew, they replicated, and they formed vast colonies. As we bring our dream ship in for a closer look at the edges of these greenish seas, we can see them. They look like strange, slimy, layered cushions of rock, living structures called stromatolites. These are mats of microorganisms, growing layer by layer towards the sunlight. For a billion years, these humble, living rocks were the undisputed kings of life on Earth. They were nothing spectacular to look at. But these tiny, simple organisms were about to perform a feat of biological alchemy that would change the world forever. A new phenomenon, a new trick, appeared with them. Living in the sunlit shallows, they evolved a way to use the energy of the sun directly as food. They became the planet's first solar-powered beings. This process, which you know by the name photosynthesis, allowed them to take sunlight, water, and carbon dioxide and convert it into the chemical energy they needed to live and grow. It was the most important invention in the history of life. And this incredible process had a byproduct. It had a waste product. As these trillions upon trillions of microorganisms soaked up the sun, they released a gas. They exhaled. And the gas they breathed out was oxygen. At first, it was just tiny bubbles rising from the slimy mats in the shallow water, a quiet, almost insignificant fizz in the vastness of the ocean. For hundreds of millions of years, this newly liberated oxygen didn't even reach the atmosphere. The oceans themselves were full of dissolved iron, and this oxygen immediately reacted with it, causing the iron to, in essence, rust and precipitate out of the water, sinking to the ocean floor. Our planet's oceans were literally rusting from within. This process created the vast banded iron formations that, billions of years later, would provide the raw material for our own age of iron and steel. This period, this Archean Eon, lasted for an almost eternal 1.5 billion years, 3 times longer than the fiery Hadean Eon before it. For all that time, life remained simple, microscopic, confined to the water. But it was busy. It was patiently, relentlessly performing its photosynthesis, slowly, bubble by bubble, changing the chemistry of the entire planet. As we hover here, at the very end of this long, quiet age, we can feel a tension building. The water is becoming saturated. It can't absorb much more of the oxygen being pumped into it. The great rusting of the oceans is nearing its end. And so, for the first time, this potent, reactive gas, this breath of life, begins to escape the water's surface in significant amounts, rising up to meet the sky. A new age is about to begin, an age defined by this powerful new addition to our atmosphere. The world is about to change again, and this time, the change will be revolutionary. For more than 1 billion years, the tiny, single-celled inhabitants of Earth's oceans had been patiently performing their quiet miracle. They had been drinking sunlight and, in doing so, exhaling a new gas into the world, oxygen. For all that time, the planet's chemistry, particularly the vast iron reserves in its seas, had absorbed this output, locking it away. But no system can absorb change forever. The oceans had finally become saturated. The great rusting was complete. Now, as we watch from our dream ship, the cup is overflowing. The oxygen, with nowhere else to go, is pouring out of the water and into the sky, beginning a process that will forever alter the destiny of our world. This new age we have entered is the longest in Earth's history, a staggering 2-billion-year-long chapter called the Proterozoic Eon, a name that beautifully means earlier life or former life. And it began with a crisis. We think of oxygen as the sweet breath of life, the very air that sustains us. But for the life that dominated the Archean world, this rising tide of oxygen was a deadly poison. The planet's first inhabitants were anaerobic, meaning they lived in the absence of oxygen and were, in fact, destroyed by it. To them, this new gas was a corrosive, terrifying force. It was the planet's first great pollution event, and ironically, it was caused by life itself. Imagine being one of those ancient microbes, perfectly adapted to a world without oxygen. Suddenly, your environment is filled with this new, aggressive element that tears your cellular structures apart. It was a planetary catastrophe, a mass extinction event that wiped out countless species of these early life forms. The very architects of this new atmosphere became its first victims. The world they had built was now hostile to them. But life, as we are beginning to see, is not just resilient, it is endlessly inventive. In the face of this crisis, a new miracle occurred. Some organisms, through random mutation and the relentless pressure of natural selection, didn't just find a way to tolerate the oxygen poison. They learned to harness its power. They evolved a new, revolutionary way of breathing called aerobic respiration. If photosynthesis was like discovering how to create a fuel source from sunlight, then aerobic respiration was like inventing a hyper-efficient engine to burn that fuel. It unlocked vastly more energy from the same amount of food than the old anaerobic methods could. Life had stumbled upon a superpower. And with this new superpower, everything changed. The extra energy allowed life to become more complex, more dynamic. For the first time, cells could afford to do more than just survive and replicate. They could specialize. They could cooperate. And this led to perhaps the most profound leap in organization since the origin of life itself, the birth of multicellularity. We can see it happening in the Proterozoic seas. Single cells, perhaps finding safety in numbers or efficiency in teamwork, began to cling together, forming colonies. Over immense spans of time, these colonies became more integrated, with different cells taking on different jobs. Some might specialize in movement, others in feeding, others in reproduction. They were no longer just a collection of individuals, they were becoming a single, coordinated organism. These first multicellular beings were still very small and simple, perhaps just tiny blobs of jelly or delicate, feathery fronds waving in the ocean currents. But they were a quantum leap beyond the microbial mats that had reigned for 2 billion years. They were the ancestors of all the complex life that would follow, the first rough drafts of the animals and plants we know today. This new miracle, this blossoming of complex life, was made possible by that once toxic gas, oxygen, which was now accumulating freely in the air. But the oxygen revolution had another, far more dramatic consequence. It sent the planet's climate into a violent tailspin. The early Archean atmosphere was rich in methane, a powerful greenhouse gas that helped keep the planet warm under a fainter young sun. But oxygen reacts with methane, destroying it. As oxygen levels rose, methane levels plummeted. It was as if someone had suddenly thrown open all the windows of a warm house in the dead of winter. The planet's thermostat was broken. Earth began to get cold. Very, very cold. And this brings us to one of the most intriguing and chilling mysteries in our planet's history. As we watch from our dream ship, we see the ice caps at the poles begin to grow. Year by year, century by century, they creep further south and north. But they don't stop. The cooling feeds on itself. The white ice reflects more sunlight back into space than dark rock or water does, which makes the planet even colder, which allows more ice to form. It's a runaway effect. The glaciers spread from the poles, they crawl down from the mountains, until eventually, the entire planet is encased in a shell of ice. We are now hovering over a world that looks like a giant, gleaming snowball, a white marble traveling through the blackness of space. It is the Snowball Earth hypothesis, a time when our planet may have been entirely, or almost entirely, frozen over, perhaps more than once during this long eon. The oceans are frozen solid, perhaps a kilometer thick. The continents are buried under colossal sheets of ice. The silence is absolute, the air thin and frigid. It is a world locked in a deep freeze. You have to wonder, how could life possibly have survived this? It seems like an insurmountable catastrophe. But life is tenacious. It finds a way. Perhaps, in the deepest parts of the ocean, near the geothermal vents we saw earlier, pockets of liquid water, warmed by the planet's inner heat, became sanctuaries. Here, in the crushing dark, life could hold on, waiting for the thaw. Or maybe, life found refuge in tiny cracks within the ice itself, or in patches of equatorial ocean that remained as slushy, unfrozen slush. For millions of years, our planet was a frozen wasteland, with its precious cargo of life clinging on by the barest of threads. What broke the spell? What could possibly melt a frozen planet? The answer, ironically, came from the very geological activity the ice was trying to suppress. All this time, even under the ice, volcanoes continued to erupt. They kept pumping gases into the atmosphere, including vast amounts of carbon dioxide. With the oceans frozen over, there was no water to absorb this CO2. For millions of years, it accumulated in the atmosphere, building up, until it created a super greenhouse effect. The planetary thermostat, once turned down to freezing, was now being cranked up to scorching. The thaw, when it came, was violent and geologically swift. The ice melted, the seas were liberated, and life, which had been hiding in the dark, could emerge once more into the sun. These cycles of deep freeze and rapid thaw may have happened multiple times, acting as an intense environmental filter, perhaps even accelerating evolution by rewarding the most adaptable organisms. And so, this immense 2-billion-year chapter, the Proterozoic, drew to a close. During its vast expanse, our planet was utterly transformed. Continents continued to drift and collide. The chemical composition of the air and oceans was permanently rewritten. Life learned to breathe oxygen and took its first bold steps towards complexity. And the entire world was plunged into, and escaped from, a global ice age of unimaginable severity. As the end of this eon neared, we can see in the thawed-out seas the first true animals beginning to appear, strange, soft-bodied creatures unlike anything alive today. The land was still naked and empty, but in the water, the stage was finally set. The long prologue, accounting for almost 90% of Earth's existence, was over. A new eon was about to begin, the age of abundant, visible life. We have now crossed the most significant threshold in the story of life. We are leaving the vast, slow, and mostly invisible world of the Proterozoic behind and entering a new eon, the one we ourselves live in, the Phanerozoic eon. The name itself is a declaration of change, meaning, visible life. For nearly 4 billion years, life on Earth was a secret, hidden away in the microscopic realm. But no longer. From this point forward, life will step out of the shadows and onto the world stage, becoming so abundant, so large, and so revolutionary that its story will be written directly into the rocks of the planet itself. We have arrived at the age of animals and plants. Our journey begins 540 million years ago, in a period that marks the first chapter of this new eon, the Cambrian. And what a chapter it is! For tens of millions of years, the seas have been home to those simple, soft-bodied creatures we saw at the end of our last chapter. But then, in a geological blink of an eye, something astonishing happened. It's an event so dramatic, so creatively fertile, that scientists call it the Cambrian Explosion. It wasn't an explosion of fire and rock, but an explosion of life itself, a biological Big Bang where nature's imagination seemed to run wild. Let's dive our little dream ship beneath the waves of a Cambrian sea. The world we enter is a bustling, alien metropolis teeming with creatures more bizarre than any science fiction writer could invent. Look there, scuttling across the muddy sea floor, trilobites. These armored, insect-like creatures are everywhere, some as small as a fingernail, others as large as a dinner plate. They are the iconic animals of this age, masters of the seabed. And look at that strange creature, walking on what looks like a dozen pairs of pointy stilts, with a row of fleshy tentacles on its back. That is the aptly named hallucigenia, a creature so weird that for decades, scientists couldn't even figure out which way was up. But not all is peaceful in this new world. For the first time, true predators are on the hunt, driving an evolutionary arms race. Floating silently above the sea floor is the apex predator of its time, the fearsome Anomalocaris. It's a creature up to a meter long with large, compound eyes, two fearsome grasping claws at the front of its head, and a strange, circular mouth that looks like a slice of pineapple lined with teeth. It is the T-Rex of the Cambrian seas, and its presence forces other animals to evolve defenses, hard shells, sharp spines, or the ability to burrow and hide. In this creative frenzy, nearly every basic body plan, or phylum, that exists today came into being. Sponges, mollusks, arthropods, and even the very first members of our own lineage, the chordates. Look closely, among the weeds, you might see a small, ribbon-like creature, no longer than your finger, swimming with a wriggling motion. That is Pikaia, and it possesses the faintest precursor to a backbone. In that humble little swimmer, we can see the ghost of our own impossibly distant ancestor. Why did this happen? Why this sudden burst of creativity after billions of years of slow, simple life? The reasons are still debated, but it was likely a perfect storm of conditions. The atmosphere was now rich in oxygen, providing the fuel for more active, complex bodies. The evolution of predation created intense pressure to innovate. And the development of hard shells and skeletons not only offered protection but also provided a framework for new kinds of bodies to be built, and crucially, left behind a treasure trove of fossils for us to find. For millions of years, this vibrant pageant of life was confined to the water. The land remained as it had been for eons, a silent, empty world of bare rock and dust. But life, full of its newfound energy and diversity, began to eye this vast, unclaimed territory. The invasion of the land was the next great chapter in our story, a challenge far greater than any faced before. For a sea creature, the land was a deadly desert. There was the crushing force of gravity without the buoyancy of water to support you, the harsh, unfiltered ultraviolet rays of the sun, and the constant threat of drying out in the open air. The first pioneers were the plants. Relatives of modern mosses and liverworts began to creep out from the water's edge, forming a thin green scum on the wet rocks. To survive, they had to evolve incredible new adaptations. They developed root-like structures to anchor themselves and absorb minerals, strong, woody stems to hold themselves up against gravity, and a waxy outer layer to seal in moisture. They became the architects of a new terrestrial world, slowly, painstakingly creating the first true soils and changing the very air the world breathed. Once the plants had established a beachhead, the animals followed. The first to venture ashore were the arthropods, the ancestors of insects, spiders, and scorpions, already equipped with a supportive exoskeleton. We can almost imagine their first tentative steps, scuttling out of the shallows for a brief moment before scurrying back, gradually adapting to breathe the air and live full-time on the land. And so, the silent continents were transformed. Over millions of years, the green carpets of moss gave way to the world's first forests, strange, alien forests of towering tree ferns, giant club mosses, and horsetails that prospered in the now oxygen-rich atmosphere. The long silence was finally broken by the buzz of giant dragonflies and the skittering of countless other ancient insects. Life was conquering the globe. But the story of the Phanerozoic Aeon is not one of simple, steady progress. It is a story of epic booms and devastating busts, of ups and downs on a planetary scale. Life would radiate and grow, branching out into millions of new species and forms. But then, time and time again, catastrophe would strike. Sometimes it was intense, prolonged volcanism that choked the air and poisoned the seas. Sometimes it was a sudden change in the climate, or a collision with a giant asteroid from space. In these moments, life experienced great setbacks. Mass extinctions would wipe out a huge percentage of all living species, resetting the evolutionary clock. The book of life was brutally edited, entire chapters erased. We call these periods by names you may have heard: the Cambrian, the Ordovician, the Triassic, the Jurassic, the Cretaceous. Each represents a unique world with its own cast of characters, and each often ended in a great extinction that paved the way for the next. Yet, the most wonderful part of this story is that after every single catastrophe, life always recovered. And often, it would come back even more diverse and resilient than before. The survivors would inherit a changed world, full of empty niches, and a new explosion of creativity would begin. As we fast forward our dream ship through these hundreds of millions of years, we see the age of fishes give way to the age of amphibians, and then the long, spectacular reign of the dinosaurs. We see continents drift and collide, mountains rise and fall, and countless species appear and vanish. Finally, after one last great catastrophic event 66 million years ago, the age of dinosaurs ends, and the path is cleared for a new class of animals to rise to prominence. And that brings us ever closer to our final destination. The stage is being set for the age of mammals, and for the coming of the great ice. For hundreds of millions of years, they had lived in the shadows. While the great dinosaurs ruled the earth, our distant mammalian ancestors were small, often nocturnal creatures, scurrying through the undergrowth, staying out of the way of the giants. They were the supporting cast in a grand reptilian drama. But then, 66 million years ago, the sky fell, the world changed, and the long reign of the non-avian dinosaurs came to an abrupt end. This mass extinction event was a terrible tragedy for many, but for the mammals, it was the opportunity of a lifetime. With the great dinosaurs gone, a world of ecological possibilities opened up. The mammals, with their unique set of skills, were perfectly poised to seize the moment. What made them so special? As we know, they are warm-blooded, allowing them to regulate their internal temperature and survive in a wide variety of climates. They have complex brains, capable of learning and adapting their behavior. And perhaps most importantly, They have a unique reproductive strategy. They have relatively few babies, but they invest enormous care in them, feeding them with milk and teaching them the skills they need to survive. This combination of adaptability, intelligence, and parental care proved to be a world-conquering formula. In the millions of years that followed the dinosaurs' demise, a period called the Paleogene and then the Neogene, mammals exploded in diversity, filling every niche the dinosaurs had left vacant, and inventing new ones. They grew to enormous sizes. Some returned to the sea, evolving into the first whales and dolphins. Others took to the trees, and some even to the air, like the bats. This was the Cenozoic era, the age of new life, but it is better known as the age of mammals. From tiny shrews to giant, rhinoceros-like beasts, they dominated the planet's landscapes. Lions, wolves, bears, horses, and the ancestors of elephants spread across the globe, their forms becoming more and more familiar to us as time went on. But as the millions of years ticked by, the world was undergoing a slow, almost imperceptible change. The hot, greenhouse climate that had characterized the age of dinosaurs was gradually cooling. Over a vast span of time, the Earth's thermostat was slowly being turned down. Great forests began to shrink, replaced by vast, open grasslands and savannas. This change in environment spurred further evolution. Grazing animals evolved complex stomachs to digest tough grasses, and predators evolved to be faster and more cunning to hunt them on the open plains. The world was becoming cooler, drier, and more modern in its appearance. And then, just as we arrive at the doorstep of our story, about 3 million years ago, a monumental geological event took place that would give the planet the final push into a new state of being. It happened in the narrow gap of ocean separating two massive continents, North and South America. For tens of millions of years, South America had been a gigantic island continent, much like Australia, with its own unique collection of terrestrial species that had evolved in isolation. The Atlantic and Pacific Oceans were connected in the middle of the Americas, allowing water to circulate freely between them. But deep beneath the waves, volcanic activity was pushing the seafloor upwards. Island after island emerged, and eventually, they coalesced. A thin, winding strip of land stitched the two continents together. The Isthmus of Panama was born. This seemingly small land bridge had two dramatic, world-changing consequences. First, it created a highway for life. For the first time, the animals of North and South America could meet. A massive biological exchange began, a two-way migration of species. Armored glyptodonts, giant ground sloths, and strange, hoofed mammals from the south ventured north. At the same time, saber-toothed cats, bears, camels, and horses from the north poured into the south. It was one of the greatest natural experiments in the history of life, a reshuffling of the biological deck on a continental scale. The second consequence was even more profound. By closing the gateway between the two largest oceans on the planet, the Isthmus of Panama completely rerouted the circulation of ocean currents. It was like closing a major artery in the planet's circulatory system. The warm currents of the Atlantic, no longer able to escape into the Pacific, were deflected northward, towards the Arctic. This new current, which we now know as the Gulf Stream, carried immense amounts of warm, moist air into the high northern latitudes. This might sound like it would make things warmer, but it had the opposite effect. All that extra moisture fell as snow. Year after year, the snow fell, piling up faster than it could melt in the short northern summers. It compacted into ice, and the great continental ice sheets began to grow. Finally, 2.6 million years ago, almost yesterday on the 4.5-billion-year timescale of our journey, the long, slow cooling of the Neogene period ended in glaciation, and a new period began. This is our period, the Quaternary. And its first, long epoch is the one we have been traveling all this time to see, the Pleistocene, known to all as the Ice Age. Now, when you hear the term Ice Age, you might picture a world perpetually frozen and dead. But that is not the case. The Pleistocene was not one long, unbroken winter. It was, instead, an age defined by cycles of cold and warmth. There were long periods of intense glaciation, where vast ice sheets would expand over the continents, followed by shorter, warmer periods, like the one we are living in today, where the ice would retreat. And far from being a time of death, the Pleistocene was an age of abundant life and incredibly fast evolution. It was the age of the great Megafauna, the mammoths, the mastodons, the saber-toothed cats, and the giant sloths. And most importantly for our story, it was the age of a new and remarkably adaptable genus of mammal that was becoming arguably the most successful at colonizing the Earth, the genus Homo, the genus that we belong to. The story of the Ice Age, with its advancing and retreating ice, its changing landscapes, and its magnificent beasts, is fundamentally intertwined with the story of our own origins. So, the stage is now fully set. The geological and climatic triggers have been pulled. A new, colder, more dynamic world has dawned. The question now is, what did this world actually look like? What would we see if we flew our dream ship over the Earth during one of its great freezes? Let us venture forward, into the heart of the Ice Age itself. From our vantage point in the silent darkness of space, our home planet looks different. The familiar swirl of blue oceans and green and brown continents is partially hidden beneath two enormous, brilliant white caps of ice, gleaming under the light of the distant sun. It looks as though winter has claimed the top of the world. And in a sense, it has. A winter that lasts for tens of thousands of years. As we zoom in, the sheer scale of this transformation is staggering. The maps of the continents we know so well would look remarkably similar in their general position. After all, 2 or 3 million years is not a very long time on a geological scale, so the continents haven't drifted very far. However, a closer look reveals a world that is profoundly, dramatically altered by the power of ice. Let's begin our tour over North America. There is no Canada to be seen. The entire country, from coast to coast, is gone, buried beneath an ice sheet of unimaginable proportions. This is the Laurentide ice sheet, a single, contiguous mass of ice centered over Hudson Bay that flows outwards in all directions. It is not a thin veneer of ice. In places, it is more than 2 miles thick. It is so heavy that its weight presses the continent's crust down into the mantle below. Further west, the Rocky Mountains are entombed by their own colossal ice sheet, the Cordilleran. This is a continent of ice, a frozen white desert larger than Antarctica today, creating its own weather, its own howling winds, its own frigid climate. The southern edge of this ice extends far into what is now the United States. Let's trace its boundary. Great modern cities that you might know would be lying crushed beneath this moving wall of ice. Boston, New York, Chicago, Seattle, all would have been under a thick ceiling of ice during these peak glaciations. Imagine standing at its edge, a towering cliff of milky white and deep blue ice rising hundreds of feet into the air, constantly groaning, cracking, and calving off house-sized chunks of ice with a thunderous roar. This is not a static feature, it is a slow-motion river of solid water, grinding and scouring the land beneath it, carving out the deep basins that will one day become the Great Lakes. Now, let's guide our dream ship across the Atlantic. The view over Eurasia is just as dramatic. A massive ice sheet covers all of Scandinavia, Finland, Ireland, and Great Britain, stretching deep into western Russia and northern Europe. Much of Siberia, too, is in a similar state. At the maximum extent of these glaciations, it is estimated that about 30% of the Earth's entire surface was covered in ice. This is why we call it the Ice Age, even though these peaks of glaciation were cyclical, and the tropical and equatorial regions, while cooler than today, remained much warmer. A question might bubble up in your mind as you gaze upon these colossal ice sheets: where did all the water to build these continent-sized glaciers come from? The Earth didn't gain more water. The answer is simple, and it changed the face of the entire planet: it came from the oceans. This glacial advance meant that huge, truly astronomical volumes of water were locked up in these continental ice sheets. The effect was like pulling the plug on a planetary bathtub. As the ice sheets grew, the sea level across the rest of the planet dropped. And it didn't just drop by a little, it could fall by as much as 300 feet, or 100 meters, lower than it is today. The implications of this were immense. A lower sea level meant there was more land surface on the planet. Many islands that we know today were no longer islands at all, they became connected by dry land to the continents. The English Channel did not exist. Great Britain was a peninsula of northwestern Europe. The islands of Indonesia became part of the Asian mainland. And most consequentially, on several occasions, a vast land bridge emerged connecting Asia and North America around the Bering Strait. This bridge, now called Beringia, was not a narrow, icy path. It was a huge, sprawling subcontinent of cold, dry grassland, 1,000 miles wide. It was a highway for life, allowing animals and, eventually, humans to cross from one continent to the other. South of the great ice sheets, the world was not necessarily a temperate paradise. In North America, a zone of permafrost, ground that continually remains frozen below 0 degrees Celsius, extended for a few hundred miles southward from the edge of the ice. In Eurasia, particularly across most of Siberia, this permafrost zone was even larger. These frozen regions act as a perfect natural freezer for scientists today. They can keep entire specimens of extinct species, like the woolly mammoth, frozen and remarkably well preserved for tens of thousands of years, a precious gift from the past. But the Ice Age was not a static deep freeze. It was a dynamic world of cycles, and the ice also melted. And when it did, the geography changed again in spectacular fashion. As the colossal ice sheets began to warm and retreat, they released unimaginable quantities of meltwater. This water was often dammed up by the retreating ice front itself or by ridges of rock and debris the glacier had bulldozed in front of it. This process created enormous glacial lakes. Let's look at one spectacular example in central North America. As the ice melted, it created a now disappeared lake called Lake Agassiz. This was no ordinary lake. At its largest, this single body of glacial meltwater was larger than the entire United Kingdom, or almost twice the size of the state of Florida. It appeared at the very end of the Ice Age and is thought to have lasted for only a few thousand years before it was catastrophically drained, leaving behind the thousands of smaller lakes that dot the landscape of Canada and Minnesota today. The very geography of places like Canada and Finland, with their abundance of lakes, still bears the scars and traces of this period of ice and meltwater. So this was the world of the Ice Age, a planet of extremes. A world of towering ice walls, of drastically lower oceans, of exposed land bridges forming new highways for life, of vast, frozen tundra plains, and of colossal, temporary lakes that appeared and disappeared in a geological heartbeat. It was a landscape constantly being reshaped by the immense power of ice and water. But it leaves us with a profound question. Why? Why did the planet's pulse beat this way, swinging between ice and warmth? What was the engine driving these incredible global cycles? Let us venture on to seek the answer. We are left with a profound and beautiful mystery. We have seen the ice advance and retreat, the sea levels fall and rise, and the great glacial lakes fill and drain. But why? Why in these great, rhythmic cycles? Why wasn't the Ice Age just one long, continuous freeze? What was the force, the hidden metronome, that kept this planetary pulse beating at intervals of tens of thousands of years? To find the answer, we must lift our gaze from the Earth itself and look to the heavens, for the secret lies in a subtle and extraordinarily complex celestial dance. It turns out that our planet's journey through space is not as simple or steady as we might think. Its relationship with the Sun, the ultimate source of our warmth and energy, is constantly changing in three very subtle, very slow, and very predictable ways. Think of it as a great cosmic clockwork, with three interlocking gears, each turning at its own majestic pace. For a long time, these were just astronomical curiosities, but scientists eventually realized that this celestial clockwork was the master switch for the Earth's ice ages. Let's look at the first of these great cosmic rhythms. It has to do with the shape of Earth's orbit around the Sun. We learn in school that the Earth orbits the Sun, but we often picture it as a perfect circle. In reality, it's a slight oval, an ellipse. And the shape of this oval isn't fixed. Over a long, slow cycle of about 100,000 years, it gently stretches, becoming more of a pronounced oval, and then relaxes back towards being a more perfect circle. When the orbit is more elliptical, the Earth's distance from the Sun varies more throughout the year, changing the total amount of solar radiation we receive. It's a very subtle change, but over thousands of years, it has a cumulative effect. Now let's consider the second rhythm. This one involves the Earth's axial tilt, or its obliquity. As you know, our planet is tilted on its axis, like a spinning top leaning to one side. This tilt is what gives us our seasons. But this tilt is not constant. Over a cycle of about 41,000 years, the Earth gently rocks back and forth, its tilt varying by a few degrees. Think of it as the Earth slowly nodding, yes, to the cosmos over an immense span of time. When the tilt is greater, the seasons become more extreme, hotter summers and colder winters. When the tilt is less, the seasons are milder. And the key to growing a great ice sheet is having mild, cool summers where the winter snow doesn't have a chance to melt away. Finally, there is a third rhythm, a gentle wobble, like a spinning top when it starts to slow down. This is called precession. As the Earth spins, it wobbles on its axis in a slow circle. This wobble determines which hemisphere is pointing towards the Sun when the Earth is at its closest point in its orbit. This changes the timing and intensity of the seasons, and it completes its own cycle roughly every 26,000 years. Now, any one of these cycles on its own is not enough to plunge the world into an ice age. The magic happens when they come into harmony. Imagine these three great, slow rhythms, the stretching orbit, the nodding tilt, and the gentle wobble, as three different musical notes playing through the cosmos. Most of the time, they are out of sync. But every so often, by pure celestial chance, their waveforms align. They converge to create a powerful chord, a moment of perfect climatic resonance. When they line up in just such a way as to minimize the amount of summer sunlight falling on the northern hemisphere, it acts as a trigger. The summers become just cool enough that the winter snows don't fully melt. The next year, more snow falls on top of the old snow. It builds up, compacts into ice, and a new glacier is born. These astronomical cycles are the pacemaker, the initial nudge that starts the process. But the Earth's own systems, its climate, its ocean currents, its wind patterns, and the composition of its atmosphere, then take that small nudge and amplify it into a massive change. The most powerful of these amplifiers is the ice itself. As we saw, white ice is highly reflective. So, as a small ice sheet grows, it reflects more sunlight back into space, which makes the local area even cooler, which allows the ice sheet to grow even bigger. It's a classic feedback loop that can run away with itself, pushing the planet into a deep freeze. And by studying the evidence left behind in the ice itself, drilling deep into the polar caps, scientists can see how the atmosphere changed along with these cycles. The tiny bubbles of ancient air trapped in the ice show that the amount of carbon dioxide and other gases in the atmosphere rose and fell in lockstep with the ice ages, further amplifying the warming and cooling. But the Earth's pulse is not always perfectly regular. A fascinating pattern change was observed to have happened right in the middle of the Ice Age. Prior to about 1 million years ago, the periodicity of the glaciations was about 40,000 years, perfectly matching the rhythm of the Earth's axial tilt. But then, a transition happened. The beat changed. The glaciations started following a new, longer, and more powerful 100,000-year cycle, which matched the rhythm of the Earth's orbital stretch. This shift to a longer, more high-amplitude cooling is one of the great unsolved puzzles of climate science, a sign that these cycles, while powerful, are not eternal and can themselves change over time. So, this was the relentless rhythm of the Pleistocene world. A slow, predictable pulse driven by the grand clockwork of the solar system and amplified by the Earth itself. For all living beings on the planet, these cycles had a huge impact on their habitat. The world was in a constant state of slow-motion flux. For plants and animals, and for the early humans we shall soon meet, these cyclical changes often meant that they had to migrate away from the advancing glaciers and frozen seas, always looking for warmer regions where they could feed themselves. It was a world that demanded adaptation and resilience above all else. And now that we understand the pulse of this incredible world, it is time to meet the creatures who lived and breathed to its beat. As we journey through the heart of the Pleistocene, one of the most striking features of this epoch is the sheer abundance and size of the animals that walk the earth. This was an age of megafauna, literally, the great beasts. And the undisputed kings of this age, the group of animals that had truly come to dominate the land, were the mammals. Ever since the extinction of the non-avian dinosaurs, mammals had been branching out, growing larger, and adapting to every environment, generally coming out on top of the food chains. Their relative intelligence, their complex social structures, and their ability to regulate their own body temperature made them incredibly successful. And in the Ice Age, this success reached its zenith. Apart from a few extinct species of these giant mammals, the animal world would have looked very familiar to us, with lions, wolves, bears, and horses roaming the land. But it is those extinct giants that capture our imagination most, and none more so than the iconic, colossal figure of the mammoth. When we think of the Ice Age, the first image that often comes to mind is that of a great, shaggy mammoth, its long, curved tusks sweeping through a snowy landscape. And for good reason. These were truly magnificent creatures. But the first thing to know is that a mammoth is not just a single species. Mammoth refers to a whole genus, a family group of related species, just as dog can refer to many different breeds. This mammoth genus, Mammothus, belongs to a broader biological family called Elephantidae, a family that also includes the two species of elephants alive today. So, when you look at a modern African or Asian elephant, you are looking at a relatively close cousin of the mammoths that walked the earth thousands of years ago. The story of the mammoths is a grand tale of migration and adaptation. The genus first appeared around 5 million years ago, and its oldest known representatives arose not in the frozen north, but in the warm regions of southern and eastern Africa. From this African homeland, successive generations of mammoths moved north, spreading out in every direction, populating vast swathes of Africa, Europe, and Asia. Eventually, around 1.5 million years ago, they made the great crossing from Siberia to North America over the Bering Land Bridge we saw earlier. They were a true global dynasty. While some mammoths could reach impressive sizes, with exceptionally large males exceeding 13 tons, most were about the size of modern elephants, not necessarily bigger. Their bodies, however, were shaped differently, often with a high, sloping back that formed a hump of fat and muscle, and a distinctive domed forehead. But their most defining feature was their tusks, which were generally much larger and more dramatically curved than those of their modern cousins. The classic, furry-coated image we have is of one particular species, the most famous of them all, the woolly mammoth. This was a late-arriving species, appearing about 400,000 years ago, and it was perfectly adapted to life in the cold, dry grasslands, the tundra and mammoth steppe, of the north. We know them so well thanks to the discovery of incredibly well-preserved frozen specimens in Siberia and North America. Standing about the size of a modern African elephant, they were covered in a thick, shaggy coat of long, dark hair over a dense, woolly undercoat, with a diet consisting mainly of grasses and ferns. They likely lived in herds, much like elephants today, with a lifespan of up to 60 years. But they did not reproduce very fast, a fact that would contribute to their downfall. The woolly mammoth was one of the last species of the Great Ice Age megafauna to disappear, with some isolated populations surviving until only about 4,000 years ago. Why did they go extinct? The reasons are complex and still debated, but it was likely a combination of two powerful forces. Firstly, they were hunted by prehistoric humans. To our ancestors, a mammoth was a source of everything, a mountain of meat that could feed a group for weeks, thick fur for clothing and shelter, and massive bones and tusks to make tools and even dwellings. Secondly, they suffered a big reduction of their habitat. They were adapted to life in cold regions, but not icy ones. They needed to eat vast quantities of grass, so when the glaciers advanced during the peak of the last glaciation, it covered their grazing lands, pushing them into smaller and smaller refuges. But mammoths were not the only elephant-like giants in the Ice Age world, especially in North America. Living there at the same time was a relative of the mammoth called the mastodon. And though they could be mistaken for one another, mastodons were not mammoths, nor even elephants. They were distant cousins. Their family lines diverged from a common ancestor around 27 million years ago, so they had been evolving separately for a very long time. So how could you tell the difference? The biggest clue was in their teeth, which tells the story of a completely different lifestyle. While mammoths had flat, ridged teeth for grinding tough grasses, mastodons had teeth with distinctive, cone-shaped cusps, perfectly suited for chewing leaves and crushing branches of trees and shrubs. This tells us that mastodons were primarily forest-dwelling animals, browsers rather than grazers. They are often depicted with a thick coat of hair like a woolly mammoth, but we don't know for sure if this was the case. Some remains have been found in warmer regions like Florida and central Mexico, where such a thick coat would seem unlikely, even during the cooler periods of the Pleistocene. Like the mammoths, it is believed they lived in herds and, like the mammoths, they too went extinct at the end of the Ice Age, possibly due to the same deadly combination of rapid climate change and hunting pressure from the newly arrived humans. To stand in the presence of a living mammoth or mastodon would have been an experience of profound awe. These magnificent, intelligent giants were a cornerstone of the Ice Age ecosystem for millions of years. But they were just two of the leading characters in this golden age of giants. In other parts of the world, and even right alongside them, other great beasts roamed, including fearsome predators adapted to hunting them. Let us move on to meet them. Our dream ship glides away from the mammoth steppes of the northern hemisphere and embarks on a long journey south, crossing the equator into a world that has been on its own evolutionary path for millions of years. We are now hovering over the sun-drenched landscapes of Ice Age Australia. Due to the deep seas that surround it, this continent was a world apart, a vast laboratory where a different kind of mammal had risen to rule, the marsupials. These are the mammals whose most distinctive characteristic is that their young are carried and nursed in a pouch. And in the isolation of Australia, marsupial life thrived, producing its own unique caste of giants. Let's descend into the open forests and savannas. What we see here looks like something from a fantasy. It is the diprotodon, the largest marsupial that ever existed. Imagine a creature the size of a hippopotamus, weighing almost 3 tons and standing nearly 7 feet tall at the shoulder. Superficially, it might have looked like a giant wombat, with a heavy-set body and a large, broad head. These were peaceful herbivores, using their powerful front teeth to munch on leaves, grasses, and roots. It's possible they had a social organization similar to what we see in elephants, with females and their young forming family groups, while adult males lived more solitary lives, fighting for mating rights. For over 1.5 million years, from 1.6 million to about 44,000 years ago, they were the biggest and most dominant mammals in Australia. But their long reign came to an end right around the time the first humans are thought to have arrived on the continent. While there is no definitive proof, the timing is highly suspicious, and it is widely believed that these giant, perhaps slow-moving and gentle creatures could have fallen prey to the new, intelligent hunters who had just made the sea crossing to their shores. Now, let us guide our dream ship back across the Pacific to the Americas, for it is time to meet perhaps the most famous and fearsome predator of the Ice Age. It is a creature whose very name evokes an image of terrifying power, the saber-toothed cat. Its proper scientific name is Smilodon, and it is important to remember that it was not a true tiger, but a distinct genus of feline predator. The Smilodon first appeared in North America, but after the Isthmus of Panama formed, it spread south with great success, colonizing South America as well. In fact, the biggest specimens have been found in South America, where a large male could have weighed between 500 and 1,000 pounds, making it far stockier and more powerfully built than any modern tiger. What made the Smilodon so iconic were, of course, its teeth. Its upper canine teeth were overdeveloped into 2 enormous, curved, serrated daggers that could be up to a foot long. Its jaw was a marvel of engineering, able to open to an incredible gape of 120 degrees, far wider than any modern cat, in order to deploy these formidable weapons. However, studies suggest these spectacular canines were probably rather fragile and not suited for struggling with prey. Instead, it is believed the Smilodon was a master of the ambush. It likely hunted in forests and bush rather than open plains, using its immense power to burst from cover, wrestle large prey like bison and camels to the ground, and then deliver a quick, precise, and fatal bite to the soft throat or belly. We don't know for sure if they lived and hunted in groups like lions or were solitary like tigers. The fossil evidence is ambiguous, leaving us with a tantalizing mystery about their social lives. Like so many of the great beasts, the Smilodon did not survive the end of the Pleistocene, disappearing about 12,000 years ago. It was probably not hunted to extinction by humans, but its fate was sealed by the disappearance of the large prey it specialized in hunting. But there was another reason its world was changing, another predator whose rise was a formidable competition for all others. Individually, they were not as strong as a Smilodon or a giant bear. But their power lay not in individual might, but in their numbers, their incredible social organization, their collaboration, and their supreme adaptability. These were the wolves. The rise of the gray wolf during the Ice Age marked a major shift in the predator landscape. They were incredibly efficient hunters, and their teamwork made them arguably the main rivals of early humans for dominance of the continents. In a way, they were a mirror image of our own ancestors, intelligent, social hunters, capable of bringing down prey many times their own size through communication and strategy. So the world of the Ice Age was a complex and competitive place. It was a world of gentle giants and colossal herbivores, but it was also a world of terrifying predators. There were the powerful ambush specialists like the Smilodon, and the highly organized, adaptable pack hunters like the wolves. The stage was filled with a rich cast of incredible animals. And now, into this world of giants and hunters, the most influential character of all is about to make its grand entrance, a creature that would learn not only to compete with the wolves and avoid the Smilodons but to change the entire planet. It is time to tell the story of the rise of the genus Homo. In the great drama of the Ice Age, a new actor has been waiting in the wings. This creature is not the largest, nor the strongest, nor the fastest. It lacks the mighty tusks of the mammoth and the terrifying fangs of the Smilodon. Yet, it possesses a quality that will ultimately allow it to outlast them all and reshape the planet to its will. This, my friend, is the story of the genus Homo. It is the story of us. For a long time, the question of our own origin was shrouded in mystery and controversy. In the late 19th century, when the theory of evolution first emerged, the idea that humans were subject to the same natural laws as any other animal was scandalous. The notion that men descended from apes seemed radical and, to many, unbelievable. After all, the gap in appearance, in posture, and in cognitive abilities between a human and a chimpanzee seemed too vast to bridge. This led many to search for a missing link, a single, undiscovered fossil that would neatly represent an intermediate stage of evolution between ape and human. But modern science, with the help of countless more fossil discoveries and the revolutionary power of DNA analysis, has let all of this behind. We now understand the story is more subtle and more beautiful than that. The current position is not that humans descended from apes, but that we are related to them through a common ancestor. It's like looking at your own family tree. You didn't descend from your cousin, but you both share the same grandparents. To find our place, We must climb up the great tree of life to the branch we share with our closest living relatives. This brings us to the great family of primates called hominidae, or the great apes. Millions of years ago, this family branched out. One subfamily, Pongini, now represented only by the orangutans of Southeast Asia, went its own way. The other subfamily, Hominini, remained in Africa, and it too began to split. First, the branch leading to the gorillas, Gorillini, diverged. Later, the subfamily split again into two final branches. One branch, Pan, includes the apes we know as chimpanzees and bonobos. The other branch is ours, Homo. This makes us a cousin branch to apes, not their descendants. A fascinating question that remains open is who, exactly, was that last common ancestor we share with chimpanzees, and when did they live? The final divergence could have happened as early as 13 million years ago, long before the Ice Age began. And it may not have been a clean break. It's possible that hybridization, the ability to reproduce between the two emerging species, went on for a very long time, perhaps until as recently as 4 million years ago. The lines were blurry for a long, long time. In any case, by the time the Pleistocene began 2.5 million years ago, the divergence was complete. A new genus had emerged on the African plains, a group of creatures that were no longer apes in the way we think of chimpanzees, but not yet human. This was the genus Australopithecus. And it is from within this group that our own genus, Homo, would eventually emerge. You have certainly heard of Lucy. Discovered in Ethiopia, Lucy is the name given to the incredibly famous and remarkably complete remains of a female individual who lived about 3.2 million years ago. She was a representative of the species Australopithecus afarensis. Her skeleton was a revelation. It showed she had long arms and was likely still comfortable in trees, but her pelvic and leg bones proved that she could, and did, walk upright on two legs. She was a creature of two worlds, the forest and the savanna, a perfect transitional form. So, is Lucy our great-great-great-grandmother? Maybe. We don't know for sure which specific species of Australopithecus is our direct ancestor, but even if she wasn't, she was at least a very close relative, a snapshot of what our ancestors were like at this pivotal moment in our history. This brings us to another great puzzle, one that has become even more contentious in recent years. Where do we draw the precise line between Australopithecus and Homo? What is the spark that defines the dawn of humanity? Historically, the answer was simple: the first use of stone tools. For decades, the advent of Homo was fixed at the moment our ancestors first picked up one stone to deliberately shape another, an event thought to have happened around 2 to 2.5 million years ago, in the early Ice Age. This was the consensus in the 1980s. But science is always discovering, always revising. More recent discoveries have thrown a fascinating complication into the story. Archaeologists have found evidence of stone tool use from more than 3 million years ago, a time when we thought only Australopithecus was around. This incredible discovery blurs the once clear distinction between Australopithecus and Homo. Does making a tool automatically make you human? Or were our more ape-like ancestors more capable and intelligent than we ever imagined? The debate continues, and it reminds us that evolution is not a series of neat boxes, but a messy, gradual, and wonderful continuum. So here we stand, at the very threshold of humanity. In the heart of Africa, a group of remarkable upright walking hominins is looking out over a world of grasslands and giants. They are learning, adapting, and perhaps, some of them are beginning to think in a new way, to see a rock not just as a rock, but as a potential tool. The dawn is breaking. The first, faint light of the human mind is beginning to glow. And out of this creative crucible, a new genus is ready to be born. From the crucible of evolution in the East and South African savanna, the first widely recognized members of our own genus, Homo, emerged. The first of these to be named was Homo habilis, a name that means handy man. He was given this name because, for a long time, he was considered the first to make and use stone tools, a skill once thought to be the very definition of humanity. While we now know the story of tool use might be older and more complex, Homo habilis was without a doubt a master of this new technology for his time. Let's imagine a day in the life of these archaic humans, who lived from about 2.4 to 1.4 million years ago. They were still relatively small and frail creatures. An adult might stand only 3 to 5 feet tall and weigh between 45 and 80 pounds. Their body proportions were still a mix of the old and the new. They had long arms relative to their body size, and hands that hinted they still may have spent a good deal of time in the safety of trees. And yet, they walked upright. They could stand and run across the open ground, though this was probably not their usual posture. They lived in a world of giants and terrifying predators, and their survival depended on their wits. It is believed they lived in small societies of a few dozen individuals and were expert scavengers. Using simple but effective stone tools they chipped themselves, they were masters of butchering. They would watch from a safe distance as a smilodon or a pride of lions brought down a large animal. Then, when the great predators had eaten their fill and moved on, the nimble Homo habilis would dart in, using their sharp stone flakes to quickly slice off meat and smash open bones to get at the nutritious marrow inside, a food source unavailable to most other animals. We know from the wear on their teeth that their diet also included a lot of fruit. There is even a tantalizing clue that they may have been the world's first architects. In 1962, a circle of stones dated to 1.7 million years ago was discovered in Africa. The rocks were piled up at regular intervals and could have been used to support poles stuck in the ground, perhaps for a simple hut or a windbreak. Was this the work of Homo habilis? It's possible, but we must remember they were not alone on the landscape. For a long time, the story of human evolution was told as a simple, linear progression. Homo habilis appeared, then evolved into the bigger and more advanced Homo erectus, who in turn evolved into us. But as with so much of our ancient history, the truth is more complex and interesting. Fossil evidence has since surfaced showing that Homo habilis and Homo erectus had coexisted for a very long time, perhaps 500,000 years. This suggests they may not have been a simple parent-child relationship in the family tree, but perhaps two separate sister lineages that branched from a common ancestor, each trying out a different strategy for survival. And what a different strategy it was. About 2 million years ago, a new kind of human appeared on the scene, and he was a game changer. This was Homo erectus, the upright man. And he truly lived up to his name. These archaic men resembled us much more closely. They had a flatter face, a more prominent nose, and possibly sparse body hair adapted for staying cool while active under the hot sun. They were significantly taller and more robust than Habilis, with adults standing anywhere from 4 feet 9 inches to over 6 feet tall and weighing up to 150 pounds. But the differences were far more than skin deep. Homo erectus represented a great leap forward in human capability. He was not just a scavenger, he was an active and highly capable hunter. He was the first known human to become an apex predator, able to hunt in coordinated groups to bring down large game. And he possessed a revolutionary new tool, fire. The controlled use of fire changed everything. It provided warmth on cold nights, kept dangerous predators at bay, and allowed for the cooking of food, which unlocked more nutrients and made digestion easier. The campfire also would have become a powerful new social center for the group. There is even evidence suggesting a growing complexity in their social bonds. They cared for injured or sick group members, a sign of true empathy and community. We don't know if they were capable of speech as we know it, but it is postulated that they could communicate with a basic proto-language, a crucial step in coordinating their complex new behaviors. And with these new skills, Homo erectus did something no hominin had ever done before. He walked out of Africa. For millions of years, the story of our lineage was confined to a single continent. But Homo erectus was the first great trailblazer, the first global citizen. There is no doubt that this species went out of Africa. Plenty of remains have been found in Asia and in Europe. Famous fossils like the Java man and Peking man are now generally considered to be part of the wide-ranging Homo erectus species. Their journey was one of the most important moments in human history, a testament to their incredible adaptability. For almost 2 million years, they were the dominant representatives of Homo on the planet, a reign far longer than our own species has yet managed. These were the true pioneers, the ancestors who first took possession of the earth and laid the foundation for all who would follow. And even their great success would eventually give way to a new chapter, and the arrival of a human even more like ourselves. The 2-million-year reign of Homo erectus was a story of incredible success, but as the middle of the Pleistocene wore on, they gradually gave way to a new species, one with even more advanced capabilities, Homo heidelbergensis. This species is now considered by many to be the common ancestor of two new and fateful branches of humanity. They developed more complex tools, including the ingenious technology of hafting, attaching a stone artifact, like a spear point or an axe head, to a handle. This required foresight and abstract thought, and it set the stage for the two most famous human species of all. From heidelbergensis, one branch evolved in Europe and Asia, adapting to the cold, fluctuating climate of the northern latitudes. These were the Neanderthals, Homo neanderthalensis. For a long time, popular culture has painted the Neanderthal as a brutish, hunched-over, unintelligent caveman. But the archaeological evidence tells a very different, and far more respectful, story. When they appeared, they were the most evolved human species on the planet. Their brain size was in the range of modern humans, and their technology was incredibly sophisticated. They were not just keeping fires burning, they could create fire at will. They built homes in caves, made simple clothes similar to blankets or ponchos, and had a variety of cooking techniques, including roasting, boiling, and smoking. They knew of medicinal plants, and there is even evidence they were capable of seafaring on the Mediterranean Sea. Perhaps most intriguingly, there are hints of a rich symbolic thought among them. While still controversial, discoveries suggest they may have made ornaments from feathers or shells, and one discovered artifact, a bare femur with carefully placed holes, could be an ancient flute, a sign of music. They may have collected unusual objects like crystals or fossils, simply for their beauty or curiosity. These were not brutish survival machines, they were complex, capable people who thrived in the harsh world of Ice Age Eurasia for hundreds of thousands of years, lasting until about 40,000 years ago. Their population was always relatively small, and this might have been a factor in their eventual disappearance, as they were likely assimilated by interbreeding with a new wave of humans arriving from the south. The fact that most modern humans outside of Africa still carry a small percentage of Neanderthal DNA is a testament to this ancient meeting of cousins. While the Neanderthals were evolving and spreading across Eurasia, a new species was appearing back in the cradle of humanity, Africa. Around 300,000 years ago, descending from the same Heidelbergensis ancestor, our own species, Homo sapiens, was born. And while we were genetically compatible enough with our Neanderthal cousins to reproduce, something was different about us. What truly distinguished Homo sapiens from all other archaic humans was a revolution in the mind. At a time estimated to be around 160,000 to 170,000 years ago, our species began to exhibit what paleoanthropologists call behavioral modernity. It was a profound shift in cognition, a series of traits that, taken together, created a new kind of human. It included the ability for complex abstract thinking, to think about things that are not immediately present. It was the ability to plan on long periods of time, not just for the next hunt, but for the changing of the seasons. And most beautifully, it was the explosion of symbolic behavior. This was the production of ornamentation and art, the expression of identity, belief, and beauty through music and dance. These were things not directly necessary for survival, but deeply necessary for the human spirit. Our ancestors began painting magnificent animals on cave walls, carving intricate figures from bone and ivory, and wearing jewelry made of shells and teeth. They were not just living in the world, they were interpreting it. Armed with this new cognitive toolkit, the first generations of Homo sapiens lived and thrived in Africa before beginning their own great journey. And this time, the expansion was unstoppable. They spread in several waves, and in a remarkably short period of time, they ended up occupying all the continents and major islands of the world, replacing or absorbing all other human groups in the process. They spread first to South Africa, then West Africa, then into the Middle East. By 65,000 years ago they were in India, and shortly after they made the sea crossing to Australia. They pushed into Europe and China, and finally, they crossed the Bering Land Bridge into the Americas, spreading all the way south to the tip of South America. By the end of the Ice Age, some 12,000 years ago, men had taken possession of Earth. As our species completed its global conquest, the planet's pulse was beating one last time for the Pleistocene. The last great glaciation was ending. The colossal ice sheets melted, sea levels rose, and the world's geography began to settle into the familiar forms we know today. This period of relative heating marks the end of the Pleistocene and the beginning of our own epoch, the Holocene. This transition also coincided with the end of the Golden Age of giants. The mammoths, mastodons, smilodons, and countless other species of megafauna that had defined the Ice Age vanished forever, likely due to a combination of the rapidly changing climate and the immense pressure from the new, highly effective global predator, us. And so our grand journey through time has reached its end. We began in a ball of fire and rock, and we end here, in the quiet warmth of the Holocene, with our own species looking up at the same stars. The story of the Ice Age is a story of fire and ice, of continents in motion, of a planet with a living pulse, and of the incredible resilience of life. It is the story of mammoths and saber-toothed cats, of Neanderthals and the first artists. It is a story that is 4.5 billion years long, and it is our story. You can now let this immense history settle. You can fall asleep, knowing that you are a part of this ancient and wonderful continuum. Sleep well, time traveler. Sweet dreams.